Going back physics 30. So we'll go through how the radius of the Earth was determined. And just using a little bit of mathematics, it can actually be quite easily determined. So back in ancient Greece, someone by the name of Eratosthenes, a mathematician, what he did was he, in his town, placed a pole. Now this is the Earth, of course, and a pole. And during some time, if the sun was directly over top, okay, the pole would not cast a shadow, right? Because the sun is coming down, rays are coming down right through the pole. And noting what time of day that was occurring, he then could go the following day, walk a certain distance. Now I'm going to be exaggerating this, going to a nearby town, placing a pole again. Now during that exact same time period, since rays coming from the sun are parallel, there would be, so let's say 12 o'clock noon at this city, no shadow. 12 o'clock noon the next day, there'd be no shadow here, but if you're this distance, because it's further away, there would be a slight shadow. And of course, I'm drawing it exaggerated. So we would have a shadow right here, and we could measure the distance from the pole to the shadow. We can also measure the distance from pole to pole between the two cities or two areas. Now here's the interesting part here. From math, you know that if you have two parallel lines bisected by a transversal, we know that these interior alternate angles are equivalent. So this, if I just redraw this over here, so we have our pole, we have that, we have our angle up there equal to this angle up here. And the interesting part here is, here we have a triangle, which goes to the center. Here we have a triangle. So if we know the distance between the shadow, the tip of the shadow of the pole and the pole itself, and if we know the distance between the two poles, what we've just done is we figured out how many times bigger this side is than this side. And similar triangles, if one side is x times bigger, all of the other sides will be x times bigger. So if we know how many times bigger this is than this, then we can take, let's say, the height of the pole multiplied by that same factor, and that would be equal to this distance, which is the radius of the Earth, or this distance, or this distance. And we can get radius of the Earth by using simple geometry, by looking at parallel lines, a line bisecting those two parallel lines. Alternate interior angles are equivalent, and of course we get two similar triangles being formed there. And if we know how many times bigger one side is than the other, hey, we can use the same thing here with the height of the pole compared to the radius of the Earth. So with that, m1 m2 over r squared, so all of a sudden now we get the radius of the Earth, masses of the object, force, and of course by the Cavendish experiment, using the masses of the spheres and the distance of separation and measuring the force, we determined big G. So if I use this now for here, looking at how I could figure out the mass of the Earth, so doing the Cavendish, determining big G from smaller masses, so now that I know the radius of the Earth, I could figure out, let's say, an object on the surface of the planet. I could figure out the force of gravity of that object. Because remember back when we did this in the previous unit, mass times acceleration of gravity. So if I know the force of attraction, if I know the big G, if I know the radius of the Earth, and if I know the mass of that object, all of a sudden I can rearrange and solve for mass 1. And of course, mass 1 represents the Earth. So figuring out the radius of the Earth, once you have that figured out, then we can figure out the mass of the Earth. So the values that you see here when we use radius of Earth and mass of Earth, that's how we can figure it out. And of course you can do that for other planets as well. Once you know the radius of the Earth and the mass of the Earth, then we can figure out other planets, Jupiter, Saturn, Venus, etc., using the same type of plan. All right, we'll see you again.